Imagine the silence of space, vast, endless, and utterly still. Then, in an instant, a soundless eruption shatters the darkness, a burst of energy so colossal it could vaporize entire star systems in the blink of an eye. These aren't scenes from a sci-fi blockbuster. They're real cosmic events, recorded across the universe, explosions so powerful they defy comprehension. Today, we're diving into the 25 most violent detonations ever witnessed in the cosmos, cataclysms that rewrite the rules of physics and leave even the brightest scientists in awe. Think about the strongest explosion you've ever seen, maybe a volcanic eruption or a nuclear blast. Now multiply that force by millions, perhaps billions, and you're still only scratching the surface of what space is capable of. From supernovas that outshine entire galaxies to mysterious gamma-ray bursts that pack more energy than our sun will emit in its entire lifetime, these events aren't just spectacular. They're the universe's way of reminding us how small we truly are and how much we have yet to understand. This journey isn't just about raw power, though. These explosions shape the cosmos itself, forging the elements that make up stars, planets, and even life. Without them, the universe would be a barren, empty void. So buckle up. We're about to witness the most extreme displays of nature's fury, each one a testament to the sheer scale and mystery of the world beyond our sky. By the end, you'll see space in a whole new light, and you might never look up at the night sky the same way again. At the top of our list sits the granddaddy of all explosions, the one that started it all. The Big Bang wasn't just a firework in the void. It was the ultimate cosmic detonation, birthing space, time, and everything we know in a single unfathomable moment. Picture this, an entire universe, infinitely hot and dense, packed into a space smaller than an atom, suddenly erupting with enough force to send matter flying outward at unimaginable speeds. In less than a second, the seeds of galaxies, stars, and planets were sown in a blaze of raw energy that makes every other explosion seem like a faint spark in comparison. What's truly mind-blowing is the evidence we've gathered to support this theory. Take the cosmic microwave background, the faint afterglow of that initial explosion, still detectable as a whisper of radiation permeating the universe. It's like finding the fingerprints of creation itself, a snapshot of the universe when it was just 380,000 years old. Then there's the way galaxies are racing away from each other, stretching the fabric of space like shrapnel from that first cataclysmic blast. Even the mix of hydrogen and helium in the cosmos lines up perfectly with what scientists predicted the Big Bang would leave behind. But here's the real kicker. This wasn't just a one-and-done event. The Big Bang set the rules for everything that came after. It determined how matter would clump together, how stars would ignite, and how the ingredients for life itself would eventually emerge. Without that initial explosion, there'd be no supernovas, no black holes, no Earth, just an endless, empty silence. So while we might never fully grasp the sheer scale of that first moment, one thing's certain: every other explosion in our countdown owes its existence to the cosmic fireworks that started it all. The cosmic aftermath of the Big Bang wasn't just a fading echo, it was the ultimate chain reaction, setting the stage for everything that followed. That initial unfathomable release of energy triggered a process called cosmic inflation, where space itself expanded faster than the speed of light, stretching the infant universe from subatomic to astronomical scales in fractions of a second. Picture a balloon inflating to the size of a galaxy before you could even blink, except this balloon carried the seeds of all future stars and galaxies within it. As the universe cooled, pure energy began crystallizing into the first particles of matter. Quarks and electrons swirled in a searing plasma so dense that light couldn't travel freely, a chaotic soup that lasted nearly 380,000 years. Then came the moment we call recombination, when temperatures dropped enough for electrons to bond with nuclei, forming the first stable atoms. That's when the cosmic fog lifted and light finally burst free. We still see that ancient glow today as the cosmic microwave background, a faint signal that fills every corner of the sky like the afterimage of creation. But the real magic happened in the unevenness of that early universe. Tiny quantum fluctuations from the Big Bang became amplified during inflation, creating slight variations in density. These cosmic wrinkles became the gravitational anchor points where matter began clumping together, eventually growing into the vast webs of galaxies we observe now. Without those microscopic imperfections, the universe would have remained a featureless expanse, no stars, no planets, just endless uniformity. Perhaps most astonishing is how this primordial explosion cooked up the universe's original elements. Within minutes, the extreme conditions fused hydrogen into helium and traces of lithium. Every atom in your body contains remnants of this nuclear alchemy. Those first simple elements became the building blocks for everything else, forged in the crucible of an explosion so vast it birthed space and time themselves. The Big Bang didn't just happen to the universe, it was the universe, unfolding in a spectacular cascade that still shapes reality today. Just when we thought the universe couldn't outdo itself, along came GRB 080916c, a gamma-ray burst so energetic it redefined the limits of astrophysics. Detected on September 16, 2008, this monstrous explosion unleashed more energy in 30 seconds than our Sun will produce over its entire 10 billion-year lifetime. To put that into perspective, it packed the equivalent punch of 9,000 supernovae detonating simultaneously, a fireball of pure destruction visible halfway across the observable universe. The Fermi Gamma Ray Space Telescope caught this cosmic scream from 7.6 billion light-years away, its sensors overwhelmed by photons carrying millions of times more energy than visible light. What made GRB 080916c so extraordinary wasn't just its raw power, it was the way it shattered expectations. The burst lasted nearly 23 minutes, with afterglows spanning X-rays to radio waves, giving scientists an unprecedented look at relativistic jets moving at 99.9999% the speed of light. These weren't just beams of radiation, they were particle accelerators on a cosmic scale, twisting space-time itself as they raced outward. What caused such a cataclysm? The leading theory points to the collapse of a hypermassive star into a newborn black hole, a stellar death so violent it funneled its entire energy budget into twin jets piercing through the dying star's remains. As those jets plowed through surrounding gas, they generated shockwaves that produced the gamma rays we observed, like cosmic fireworks echoing across billions of years. But here's the chilling part. If a burst like this happened within our galaxy, even thousands of light-years away, its radiation could strip Earth's ozone layer and trigger mass extinctions. Luckily, GRBs of this magnitude are rare, occurring perhaps once per galaxy every million years. Yet their existence proves the universe operates on a scale of violence we're only beginning to measure, a reminder that the cosmos doesn't just create life. It also holds the power to erase it in a blink of gamma-ray fury. Gamma-ray bursts aren't just random flashes in the cosmic dark. They're the dying screams of stars meeting violent ends, and the physics behind them is more extraordinary than most sci-fi. Picture a massive star 20 to 30 times heavier than our Sun, burning through its nuclear fuel at a breakneck pace. When such a star reaches the end of its life, its core collapses under its own gravity in seconds, not with a whimper, but with the most energetic implosion the universe can muster. At that critical moment, two things happen almost simultaneously. The core crushes down into either a neutron star or a black hole, while the outer layers rebound in a supernova explosion visible across galaxies. But for the rarest, most powerful stars, the story doesn't end there. Here's where it gets wild. As the core collapses, some of the star's remaining energy gets funneled into twin jets, narrow beams of plasma, heated to billions of degrees and accelerated to nearly light speed by the newborn black hole's insane magnetic fields. These jets drill through the collapsing star like cosmic blowtorches, and when they finally break free, they unleash a pulse of gamma radiation so intense it outshines the rest of the universe combined. That's the gamma ray burst. We detect a lighthouse beam of pure annihilation sweeping across space. Yet even this doesn't fully explain their ridiculous energy. The secret lies in relativity. As those jets accelerate to within a hair's breadth of light speed, time and space warp around them, concentrating their energy into an impossibly narrow cone. From our perspective, that focusing effect makes the burst appear thousands of times brighter than it would otherwise. It's nature's ultimate optical illusion, turning an already catastrophic explosion into the brightest beacons in creation. But not all gamma-ray bursts come from collapsing stars. Some arise from neutron star mergers, another universe-shaking event. When two of these ultra-dense stellar corpses spiral into each other, their collision sends gravitational ripples through space-time while spraying out jets of gamma rays and heavy elements like gold and platinum. These kilonova bursts are shorter but equally violent, proving the cosmos has multiple ways to produce light-speed fireworks. What makes these events so mind-bending is their sheer efficiency. A typical gamma-ray burst converts more energy into radiation in seconds than our Sun will emit over 10 billion years, all because of perfectly tuned chaos. A collapsing star, a newborn black hole, and relativistic jets sculpted by physics we're still struggling to decode. These aren't just explosions, they're cosmic laboratories revealing the extreme limits of what matter and energy can do when pushed to the brink. SN 2006G wasn't just another supernova, it was a cosmic anomaly so bright it forced scientists to rewrite the rulebook on stellar explosions. When this behemoth erupted in the galaxy NGC 1260, located 240 million light-years away, it outshone its entire host galaxy by a factor of 50, burning with the intensity of 50 billion suns at its peak. For 70 days, it dominated the night sky in hypothetical visibility, a testament to the sheer scale of its devastation. This wasn't just a star dying, it was a star self-destructing with unprecedented violence, blasting apart in a way that left astrophysicists scrambling for explanations. What made SN 2006G so baffling was how it defied traditional supernova models. Most supernovae fade after a few weeks, their light powered by the radioactive decay of nickel-56 forged in the explosion. But this hypernova kept glowing ferociously for months, suggesting an entirely different energy source. The leading theory, a pair instability supernova, a runaway thermonuclear reaction so extreme it tears the star apart from the inside out. Picture a star so massive, at least 150 times heavier than our Sun, that its core becomes hot enough for gamma rays to spontaneously convert into matter. These gamma rays normally provide the pressure that keeps the star from collapsing, but when they transform into electron and positron pairs, that stabilizing pressure vanishes. The result, catastrophic collapse followed by a thermonuclear chain reaction that obliterates the entire star, leaving no remnant behind, no black hole. No neutron star, just pure stellar annihilation. But here's where it gets even stranger. SN 2006G's light curve showed peculiar bumps and plateaus, hinting that the explosion may have slammed into dense shells of material ejected by the star years before its death. This points to a potential evolutionary quirk, a supernova imposter phase where the star violently ejected layers of gas before its final detonation, like a cosmic countdown to apocalypse. Such behavior aligns with theories about extremely massive stars, possibly even the first generation of stars in the universe, which lived fast, burned bright, and died in explosions that seeded the cosmos with heavy elements. The implications are staggering. If confirmed as a pair instability supernova, SN 2006 GY offers a living glimpse into the depths of the universe's earliest stars, monsters hundreds of times the Sun's mass that shaped the chemical makeup of galaxies. It's a rare window into an era when the cosmos operated on a scale of violence we can barely imagine, where stars didn't just die, they vaporized themselves in explosions that make modern supernova look like firecrackers. And while hypernova like this are vanishingly rare in today's universe, their existence proves one thing. When it comes to cosmic detonations, the universe still has tricks up its sleeve that defy all our expectations. In the mid-19th century, astronomers witnessed something bizarre, a star in the southern constellation Carinae suddenly flaring to become the second brightest object in the night sky, outshone only by Sirius. This wasn't just any star. Eta Carinae, a hypergiant with over 100 times the mass of our Sun, had entered its death throes in the most spectacular fashion imaginable. Between 1837 and 1856, it unleashed the Great Eruption, a titanic outburst that blasted away 20 solar masses of material at speeds approaching 7 million miles per hour. Yet, against all odds, Eta Carinae survived. To this day, it remains one of space's greatest unsolved mysteries, a star that should have died but didn't. What made the Great Eruption so extraordinary was its light curve, a jagged, erratic pattern unlike anything seen in a typical supernova. Instead of a single bright peak followed by gradual fading, Eta Carinae flickered like a cosmic strobe light with brightness fluctuations spanning decades. At its peak, it released as much visible light as a supernova, yet the star remained intact, shrouded in an expanding cloud of its own debris. That debris now forms the homunculus Nebula, an hourglass-shaped structure glowing with the echoes of that violent event, each lobe stretching nearly a light year across. Peering into this nebula is like opening a time capsule from the explosion itself, with light echoes still bouncing off distant dust clouds over a century later. So why didn't Eta Carinae go supernova? The answer may lie in its unstable dual-core structure. Many astronomers believe Eta Carinae isn't just one star but two, a pair of massive stellar siblings locked in a deadly gravitational dance. The primary star is so unstable that it occasionally nears the Eddington limit, the point where radiation pressure overwhelms gravity, causing it to shed entire solar masses in explosive fits. During the Great Eruption, the star may have momentarily crossed this threshold, ejecting colossal amounts of material without fully destroying itself. Think of it as a stellar pressure valve blowing off steam just on a scale that dwarfs all human comprehension. But the story doesn't end there. Hubble observations reveal intricate knots and filaments within the homunculus, suggesting multiple eruptions before and after the 19th century event. Even now, Eta Carinae continues to behave erratically, with X-ray flares hinting at violent collisions between stellar winds from its two stars. Some theorists speculate that the Great Eruption was merely a preview, that the star is still building toward an inevitable supernova or even a hypernova, possibly within our lifetimes. If that happens, it would shine so brightly it could cast shadows on Earth, rivaling the moon in our night sky. The legacy of Eta Carinae's explosion isn't just scientific, it's a humbling reminder that the universe operates on its own timetable. This star defied expectations, offering astronomers a front-row seat to a stellar tantrum that rewrote the rules of stellar evolution. Whether it's biding its time or gearing up for an encore, one thing's certain: when Eta Carinae finally does meet its end, it won't go quietly. It'll leave the universe with a bang worthy of its explosive reputation. In the crisp autumn skies of 1572, a new star blazed where no star had been seen before, a celestial intruder so bright it outshone Venus and could be spotted even in daylight. Danish astronomer Tycho Brahe wasn't the first to notice it, but his meticulous observations of this stellar nova would change astronomy forever. What he witnessed wasn't a star being born, as many believed, but a star meeting its explosive end, a supernova now bearing his name. Tycho's supernova wasn't just a dazzling light show. It was a cosmic revolution, shattering the ancient dogma that the heavens were perfect and unchanging. For centuries, Western science had clung to Aristotle's idea of an immutable celestial sphere, where nothing ever changed beyond the moon's orbit. Comets were dismissed as atmospheric phenomena, and the notion of stars appearing or disappearing was heresy. But Tycho's measurements proved otherwise. His careful records showed the newcomer lacked parallax, meaning it wasn't a nearby object like a comet, but something far beyond the planets. Here was definitive proof that the so-called fixed stars could indeed change, and violently so. The implications rippled through academia like shockwaves, paving the way for Kepler's laws and eventually Newton's physics. Modern telescopes reveal the aftermath of that 16th century spectacle, a 15-light-year-wide bubble of expanding debris still hurtling outward at nearly 6 million miles per hour. Chandra X-ray observatory images show a jagged sphere of multimillion-degree gas, glowing with elements like silicon and iron forged in the explosion's fury. At its heart lies what's left of the star, an invisible compact object, likely a neutron star, though no pulsar has been detected. The remnants' asymmetry tells a chaotic story. The original white dwarf that detonated may have consumed a companion star unevenly, triggering a lopsided detonation. What makes Tycho's supernova particularly fascinating is its classification as a type Ia, a cosmic bomb with near-identical brightness wherever it occurs. These standard candles became vital tools for measuring cosmic distances, leading to the Nobel-winning discovery of dark energy. Yet recent studies suggest even these predictable explosions have quirks. Spectroscopy of Tycho's remnant reveals clumps of material moving at different speeds, hinting that the white dwarf may have ignited multiple times before its final cataclysm. It's a reminder that while nature provides patterns, it rarely follows them perfectly. The legacy of SN 1572 extends beyond science. Cultural records from Korea, China, and Europe describe its appearance, proving how a single cosmic event can leave fingerprints across human history. Tycho himself immortalized it in his book De Nova Stella, blending precise data with poetic awe, a fitting tribute to an explosion that didn't just light up the sky but illuminated the path to modern astronomy. Centuries later, that fleeting starlight still teaches us the universe is anything but static. It's a seething, dynamic arena where change is the only constant, and sometimes it takes a star's violent death to show us the way forward. Just 32 years after Tycho's supernova stunned Renaissance Europe, the cosmos delivered an encore, another brilliant star appearing where none had been seen before. This time, it was Johannes Kepler who turned his gaze upward, documenting an explosion so luminous it rivaled Jupiter in the night sky. SN 1604, now known as Kepler's supernova, wasn't merely a repeat performance. It was a cosmic event that deepened astronomy's most urgent questions: how stars live, die, and reshape the universe around them. Unlike Tycho's supernova, which lacked a visible remnant for centuries, Kepler's left behind a sprawling debris field that modern telescopes can dissect in exquisite detail. Located 13,000 light-years away in the constellation Ophiuchus, this remnant spans 14 light-years and glows in X-rays as expanding shockwaves heat surrounding gas to millions of degrees. Chandra observatory images reveal a football-shaped structure rich with silicon, sulfur, and iron, the ashes of a white dwarf star that met its end in a thermonuclear firestorm. Kepler's supernova holds a special place in the cosmic catalogue as a textbook-type Ia explosion, a detonation so precise it serves as a standard candle for measuring the universe. These supernovae occur when a white dwarf, the dense corpse of a sun-like star, siphons too much mass from a companion, pushing past the Chandrasekhar limit. At that critical threshold, runaway fusion ignites, obliterating the star in a blast of uniform brightness, but Kepler's remnant tells a murkier story. Its asymmetrical shape and chemical fingerprints suggest the white dwarf may have merged with another star rather than slowly accreting material, a violent tango that could explain its unusual energy output. The historical record adds another layer of intrigue. Kepler's meticulous notes describe the new star's color shifting from reddish to pearly white, an observation modern astronomers link to light interacting with dust clouds near the explosion. Meanwhile, Korean and Chinese astronomers documented its visibility for over a year, with one account noting it eventually faded, like a carrion-covered fish, a poetic nod to the way stars dissolve back into the cosmic dark. What makes SN 1604 truly transformative is its timing. Appearing on the cusp of the scientific revolution, it fueled debates about celestial mechanics just as Galileo was turning his telescope to the heavens. Kepler himself used the supernova to argue against the Aristotelian cosmos, proving that change wasn't confined to Earth's atmosphere. Centuries later, we now see this explosion as more than a historical curiosity. It's a Rosetta Stone for deciphering stellar deaths, a reminder that even the most predictable cosmic events hide layers of complexity waiting to be uncovered. As we study Kepler's remnant today, we're not just piecing together the fate of a single star. We're retracing the steps of astronomers who, without telescopes or spectrometers, recognized these explosions as messengers from a universe far stranger than they dared imagine. The light that faded from their skies in 1606 still speaks to us not just in X-rays and infrared, but in the enduring quest to understand the forces that forged our place in the cosmos. In July 1054, Chinese astronomers recorded a guest star in the constellation Taurus, a celestial visitor so bright it remained visible in broad daylight for 23 days and glowed at night for nearly 2 years. What they witnessed was SN 1054, a supernova explosion that birthed one of the most studied objects in the cosmos, the Crab Nebula. Today, this expanding cloud of gas and dust stretches nearly 11 light-years across, a cosmic crime scene where the death throes of a massive star are still unfolding nearly 1,000 years later. But the real wonder lies at its heart, a pulsar spinning 30 times per second, blasting out beams of radiation like a lighthouse with the power of 1,000 suns. The Crab Nebula isn't just a pretty remnant, it's a particle accelerator on a galactic scale. Chandra X-ray images reveal intricate tendrils of plasma, energized by the pulsar's intense magnetic field and whipped into chaotic motion at half the speed of light. Filaments of ionized gas glow in hues of red and blue, each strand tracing shockwaves from the original explosion that still ripple outward at over 9 million miles per hour. Even the nebula's eerie glow isn't passive, it's synchrotron radiation, produced by electrons spiraling along magnetic field lines at near light speeds, a phenomenon so efficient it converts kinetic energy into light with almost no waste. At the center of this maelstrom sits the Crab Pulsar, a city-sized neutron star packing more mass than our Sun into a sphere just 18 miles wide. Born from the supernova's collapsed core, this ultra-dense remnant rotates so fast its surface moves at 7% the speed of light, generating a magnetic field 1 trillion times stronger than Earth. Every rotation flings charged particles into the surrounding nebula, powering emissions from radio waves to gamma rays. What makes this pulsar extraordinary isn't just its speed, it's the precision of its pulses, arriving every 33 milliseconds with atomic clock regularity, making it the universe's most reliable metronome. Yet the Crab's greatest surprise came in 2011, when the Fermi Gamma Ray Space Telescope detected gamma-ray flares from the nebula, sudden bursts of energy exceeding 100 million electron volts. These eruptions defy conventional physics, suggesting particles are being accelerated to extreme energies within the nebula's tangled magnetic fields. Some theorists speculate the flares arise from magnetic reconnection, a process where field lines snap and realign, catapulting particles to near light speed in milliseconds. It's a cosmic powerhouse operating on principles we're still struggling to decode. The legacy of SN 1054 stretches far beyond astronomy textbooks. Its light echo has been used to measure the nebula's three-dimensional structure, while the pulsar serves as a laboratory for testing Einstein's general relativity. Even the nebula's expansion rate, meticulously tracked since its discovery, helped confirm that supernova remnants don't just coast, they're propelled by energy from their central pulsars. From ancient court astronomers to modern astrophysicists, this explosion has served as a Rosetta Stone for stellar death, a reminder that sometimes the most violent events in the cosmos leave behind the most enduring lessons. Cassiopeia erupts across the cosmos like a fireworks finale frozen in time, a supernova remnant so young and violent its shockwaves still ripple through interstellar space at 15 million miles per hour. Located 11,000 light-years away in the constellation Cassiopeia, this expanding wreckage spans 10 light-years and glows with the aftermath of a star's catastrophic self-destruction roughly 350 years ago. But here's the twist: no one on Earth recorded seeing it. The light from this colossal detonation should have outshone Venus in our skies around 1670, yet historical records show nothing. The answer lies in cosmic dust, thick clouds between us and the explosion that absorbed its visible light, rendering it invisible to 17th century astronomers. What makes Cassiopeia extraordinary isn't just its explosive power, but the forensic evidence it left behind. Chandra X-ray observatory images reveal a debris field resembling a shattered glass sphere, with filaments of silicon, argon, and iron flung outward in intricate patterns. These elements, forged in the star's core during its final seconds, now trace the physics of the blast itself. The remnant's asymmetry tells scientists this wasn't a clean explosion. The star likely convulsed in uneven pulses, ejecting material in violent spurts before its core collapsed into a neutron star. That dense remnant, barely 20 kilometers across, now sits off-center from the expanding debris, a silent witness to the chaos that birthed it. But the real breakthrough came with the discovery of Cassiopeia's light echoes. When the supernova's initial flash reached Earth, some photons bounced off interstellar dust clouds, taking longer paths to reach us. Like cosmic ripples in a pond, these delayed reflections allowed astronomers to pinpoint the explosion's date by comparing echoes from different dust layers. Infrared telescopes caught these ghostly signals in 2005, revealing light that had traveled an extra 300 years, finally solving the mystery of why no one saw the star's death in real time. The echoes do more than date the explosion. They act as time machines. By analyzing the spectral fingerprints in these reflected light waves, researchers reconstructed the supernova's original light curve, confirming it was a Type Ib explosion, a rare breed where a massive star sheds most of its hydrogen envelope before detonating. This makes Cassiopeia a missing link between ordinary supernova and more exotic stellar deaths, offering clues about how stars distribute heavy elements across galaxies. Today, the remnant continues to evolve. Radio telescopes detect knots of oxygen-rich gas racing outward at hypersonic speeds, while the neutron star's powerful wind carves cavities in the surrounding debris. It's a dynamic laboratory where we can watch stellar afterlife in action, a violent yet beautiful reminder that even in death, stars shape the cosmos. Cassiopeia may have hidden its light from 17th century skywatchers, but today it screams its secrets across the electromagnetic spectrum, proving some cosmic explosions refuse to fade quietly into the dark. SN 1994D appeared in the outskirts of galaxy NGC 4526 like a cosmic flare gun, an unnervingly perfect explosion that would become one of history's most pivotal supernova. Discovered on March 7, 1994, This Type Ia blast wasn't the brightest or closest of its kind, but its timing made it legendary. Caught just 11 days before peak brightness, it offered astronomers a front-row seat to the entire explosive sequence, from initial spark to fading ember. What unfolded wasn't just a star's death throes, it was a masterclass in cosmic geometry, proving these explosions could serve as the universe's tape measure. The brilliance of SN 1994D lies in its textbook purity. As a Type Ia supernova, it followed the script with near-mathematical precision. A white dwarf star stealing mass from a companion until it hit critical density, triggering runaway nuclear fusion that vaporized the star in a predictable, repeatable flash. That consistency is what makes these explosions so valuable. Since they all reach roughly the same peak brightness, any variations in how dim they appear from Earth directly correlate with distance, like a series of identical lighthouses scattered across a dark ocean. By comparing 1994D's observed brightness with its known intrinsic luminosity, astronomers could nail down NGC 4526's distance at 55 million light-years with unprecedented accuracy. But this supernova's legacy extends far beyond a single measurement. It became a cornerstone in the chain of evidence leading to the Nobel Prize-winning discovery of dark energy. When combined with later Type Ia observations, 1994D helped reveal something disturbing. Distant supernovae were fainter than expected, suggesting the universe wasn't just expanding, it was accelerating. This wasn't a minor tweak to cosmology. It meant some mysterious repulsive force, now called dark energy, was stretching space itself apart. 1994D's pristine light curve became a benchmark for calibrating these measurements, proving that even modest-looking stellar explosions could upend our understanding of reality. Hubble Space Telescope images of the supernova tell another story, one of forensic astronomy. Unlike messy core collapse supernova, 1994D left no neutron star or black hole behind. Instead, its expanding debris field dissipated cleanly, enriching the galaxy with iron and other heavy elements. Spectra revealed the telltale signatures of silicon and sulfur, elements forged in the white dwarf's thermonuclear fireball, while the absence of hydrogen confirmed the progenitor had stripped its outer layers before detonating. It's these chemical fingerprints that help astronomers distinguish Type Ia explosions from their stellar cousins. What makes 1994D truly timeless is how it embodies the scientific method. Here was an explosion observed with such meticulous detail that it became a Rosetta Stone for measuring cosmic expansion. A single day to point in a revolution that revealed 70% of the universe's energy is missing. Every time astronomers use a Type Ia supernova to probe dark energy's grip on the cosmos, they're standing on the shoulders of this unassuming blast from 1994. Not bad for a dying star no one had heard of until it erased itself in a flash of brilliance. V838 Monocerotis didn't explode, it erupted in a way that left astronomers utterly perplexed. In January 2002, this unassuming star in the constellation Monoceros, previously too faint for most telescopes, suddenly flared to become 600,000 times brighter than our Sun. But unlike a supernova's violent self-destruction, V838 Mon's outburst was bizarrely slow, its light curve pulsing over months like a cosmic heartbeat before fading into obscurity. The event defied every known stellar explosion model, presenting a celestial puzzle so strange it spawned entirely new theories about how stars can behave when pushed to their limits. The real showstopper came after the initial eruption. As light from the blast traveled outward, it illuminated vast shells of dust surrounding the star, a phenomenon called a light echo. Hubble's images of these expanding halos look like something from a dream. Concentric rings of glowing debris expanding at light speed, each one a snapshot of the explosion's light interacting with different layers of cosmic dust. This three-dimensional time-lapse revealed structures spanning 6 light-years across, turning what could have been a fleeting event into a years-long light show. So what caused this cosmic anomaly? The leading theories read like astrophysical fan fiction. One suggests V838 Mon is actually two stars, a massive blue giant and a smaller companion, that spiraled into each other in a delayed merger. As they combined, hydrogen from the outer layers triggered a thermonuclear chain reaction, not in the core but across the star's surface, creating that unusual prolonged brightening. Another hypothesis proposes the star devoured its own planets in a fit of cosmic gluttony, with Jupiter-sized bodies plunging into its atmosphere and unleashing titanic shockwaves. But the most compelling clue lies in V838 Mon's aftermath. Unlike Supernova, the star survived its ordeal, settling into a cool, hypergiant state shrouded in mystery. Spectroscopic analysis shows it's rich in lithium, an element usually destroyed in stellar interiors, hinting at deep material mixing during the outburst. The event may represent a rarely seen transitional phase in stellar evolution, where massive stars undergo violent convulsions before settling into their final forms. What makes V838 Mon's outburst so revolutionary isn't just its strangeness. It challenges our definitions of stellar explosions, proving that not all cosmic detonations fit neatly into textbooks. Sometimes the universe writes its own rules and leaves us scrambling to decode them. On February 24, 1987, a star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, erupted with the force of 100 million suns. Supernova 1987 wasn't just another distant flash in the sky. It was the closest observed stellar explosion since Kepler's supernova in 1604, visible to the naked eye despite being 168,000 light-years away. But what made this cataclysm revolutionary wasn't its brightness, it was the cascade of scientific firsts it delivered, rewriting our understanding of how massive stars die. The initial burst of neutrinos told a story no optical telescope could. 3 hours before the light reached Earth, detectors buried deep underground from Japan's Kamioke and to Ohio's IM registered 24 ghostly particles passing through our planet. These weren't ordinary cosmic rays, they were the dying screams of the progenitor star's collapsing core, a neutrino pulse carrying away 99% of the supernova's energy in 10 seconds. For the first time in history, humanity had captured direct evidence of a star's core transforming into a neutron star, confirming decades-old theories about supernova mechanics. The numbers still stagger physicists today. 10 to the 58th neutrinos emitted, a temperature of 200 billion degrees at collapse, and a newborn neutron star spinning at nearly 1,000 times per second. Hubble's later observations revealed an even more astonishing structure, 3 concentric rings of glowing gas spanning nearly 1 light-year across, resembling a celestial bullseye. These weren't remnants of the explosion itself, but relics of the star's final centuries, when the blue supergiant progenitor, Sanjalik-69202, shed layers of material in erratic outbursts. The inner ring, glowing pink with hydrogen, marks where the supernova's shockwave began slamming into pre-ejected gas at 30 million miles per hour, creating X-ray hotspots visible to orbiting telescopes. Meanwhile, ultraviolet light from the blast ionized the outer rings, making them fluoresce like neon signs, a delayed light show unfolding decades after the initial explosion. Yet 1987 still guards its deepest secret. While models predicted the collapsed core should have formed a pulsar, no neutron star has been conclusively detected. Some theorize it's hidden behind thick dust, while others suggest it might have collapsed further into a black hole, an outcome that would challenge our models of stellar evolution. What we do know is this supernova became nature's perfect laboratory, proving that stars don't die quietly. They go out with a bang that echoes across centuries, leaving behind cosmic puzzles for generations to solve. In September 1859, British astronomer Richard Carrington witnessed something unprecedented, a blinding white flare erupting from the sun's surface, so intense he initially thought his telescope had caught fire. Little did he know, he just documented the most powerful solar storm in recorded history, an explosion of plasma and magnetism now known as the Carrington Event. What followed wasn't just a celestial light show, it was a geomagnetic apocalypse that lit telegraph wires on fire, sparked auroras visible near the equator, and bathed the planet in currents strong enough to power modern cities for years. If a storm like this struck today, our hyper-connected world could face technological chaos on a scale we've barely prepared for. The physics behind the Carrington Event reads like a disaster movie script. That initial solar flare, a tangled release of magnetic energy, unleashed a coronal mass ejection, a billion-ton cloud of charged plasma racing toward Earth at over 4 million miles per hour. When it slammed into our magnetosphere just 17 hours later, 3 times faster than typical solar storms, it compressed Earth's magnetic field like a punch to the gut. The resulting geomagnetic storm induced currents in anything metal, especially telegraph systems, the Victorian era's internet. Operators reported sparks leaping from equipment, papers igniting on desks, and some machines continuing to send messages even after being disconnected from power. In Havana, auroras burned so bright locals mistook them for sunrise and began their morning routines at midnight. But here's what keeps space weather experts awake at night. A modern repeat could collapse critical infrastructure worldwide. Unlike 1859's simple telegraph lines, today's power grids stretch thousands of miles, acting as perfect antennas for geomagnetically induced currents. Transformers, massive, expensive pieces of equipment that take years to replace, would overheat and fail, triggering cascading blackouts. Satellite communications could fry in the radiation storm, GPS signals would distort by hundreds of feet, and underground pipelines might corrode from electrification. Studies estimate the economic toll could reach trillions, with recovery taking years as nations scramble to replace fried electronics across continents. The Carrington Event wasn't a fluke, it was a warning. Solar superflares of this magnitude recur roughly every 150 years, meaning we're statistically overdue. Unlike hurricanes or earthquakes, these space storms give no visceral warning. One quiet afternoon, a flash of light on the sun could spell disaster 18 hours later. While agencies now monitor solar activity, our defenses remain fragile. Shielding entire power grids isn't just costly. It's a geopolitical puzzle requiring global cooperation. Perhaps most humbling is how this 19th century explosion redefines natural disaster. The sun doesn't need to vaporize us with a supernova. A burp of misplaced magnetism could plunge civilization into darkness, proving that sometimes the universe's quietest explosions pack the loudest punches. October 2003 wasn't just another Halloween, it was the month the sun went on a rampage. Over a 2-week period, our closest star unleashed a barrage of solar storms so intense they temporarily blinded satellites, scrambled GPS signals, and painted the northern lights as far south as Florida. These weren't ordinary space weather events, they were X-class solar flares, the most powerful category, each packing the energy of billions of atomic bombs. What made this storm sequence extraordinary wasn't just its ferocity, but how it exposed humanity's growing vulnerability to our star's violent mood swings. The chaos peaked on October 28 with an X-17.2 flare, one of the strongest ever recorded. Unlike Earth-bound weather, solar flares travel at the speed of light, reaching our planet in just 8 minutes. This particular eruption hurled a coronal mass ejection toward Earth, a billion-ton cloud of charged particles racing at 5 million miles per hour. When it collided with our magnetosphere, the results were apocalyptic for anything relying on electronics. The European Space Agency's Mars Express spacecraft temporarily went blind as radiation fried its star-tracking navigation system. Closer to home, airlines rerouted flights over polar regions to avoid radiation hazards for passengers and crew, while half of NASA satellites reported sensor malfunctions or automatic shutdowns. But the most stunning effects were visible to the naked eye. Auroras typically confined to polar latitudes erupted over Texas, with shimmering crimson curtains so vivid they triggered 911 calls from panicked residents mistaking them for wildfires. In Europe, the northern lights glowed bright enough to cast shadows, illuminating landscapes with an eerie green hue rarely seen since the Carrington Event. These displays weren't just beautiful anomalies, they were proof of Earth's magnetic field buckling under the onslaught, allowing solar particles to penetrate deeper into our atmosphere than usual. What makes the Halloween storms a wake-up call is how they foreshadowed modern dependencies. In 2003, smartphones were barely mainstream and the Internet of Things didn't exist. A repeat today could cripple undersea internet cables, distort financial markets reliant on GPS timing, and disrupt emergency communications, all while exposing astronauts and high-altitude travelers to radiation levels comparable to chest X-rays every hour. Scientists later calculated the total energy released during this period equaled 10,000 times the world's nuclear arsenal, a reminder that the quiet yellow disk in our sky remains the solar system's ultimate power plant. Yet these storms also gifted researchers an unprecedented dataset. Satellites like SOHO and ACE captured every twist of the sun's magnetic fields, helping refine space weather forecasts. We now know such extreme activity often stems from sunspot regions with complex magnetic configurations, knots of magnetic energy that snap like over-twisted rubber bands. The 2003 events proved these eruptions aren't random but follow patterns we're slowly deciphering. As the sun approaches its next activity peak in 2025, the Halloween storms serve as both a warning and a lesson that our technologically woven world hangs by a thread woven from the sun's turbulent magnetic fields. On the night of August 28, 2015, the unblinking eye of a backyard telescope in Japan caught something extraordinary, a pinprick of light where none had been before, nestled in the spiral arms of our neighboring Andromeda galaxy. This wasn't just any twinkle in the cosmic dark, it was SN 2015G, a supernova detonating 2.5 million light-years away, close enough, in astronomical terms, to feel like it happened right next door. What followed was a golden moment for amateur astronomers worldwide, as one of the nearest and brightest extragalactic supernovae in decades became visible through nothing more than a decent pair of binoculars. This cosmic flare belonged to a rare breed known as a type Ib supernova, the violent death of a massive star that had already shed its outer hydrogen envelope, likely stripped away by powerful stellar winds or a companion star's gravitational tug. Unlike the more common type Ia explosions from white dwarfs, type Ib events reveal the bare helium core of a star that lived fast and died young, collapsing under its own weight when nuclear fusion could no longer hold back gravity's relentless pull. Spectroscopic analysis confirmed the telltale signatures of helium and heavy elements like oxygen and calcium, painting a portrait of a progenitor star at least 20 times more massive than our Sun. What made this explosion truly special was its accessibility. Most supernovae are spotted in distant galaxies, appearing as faint specks even through professional telescopes. But SN 2015G reached peak magnitudes visible to backyard stargazers, an ephemeral flicker briefly outshining the combined light of Andromeda's 100 billion stars. Amateurs across Europe and Asia raced to document its rise, with some capturing time lapses of the supernova brightening hour by hour. Their observations proved invaluable to professionals, filling gaps between scheduled telescope observations and helping refine models of how these stripped envelope stars meet their end. The supernova's position within Andromeda's star-forming regions added another layer of intrigue. Located near a dusty spiral arm, its light interacted with interstellar material on its way to Earth, creating subtle dimming effects that revealed clues about the galaxy's makeup. As the explosion faded over weeks, Hubble's keen eye scrutinized the site, searching for any surviving companion star or evidence of pre-explosion outbursts that might explain why the progenitor shed its hydrogen shell so completely. For astronomers, SN 2015 G was a fleeting laboratory for studying stellar death. For skywatchers, it was a once-in-a-generation chance to witness cosmic violence from another galaxy with their own eyes, a humbling reminder that the universe's grandest explosions aren't just abstract events in distant space. Sometimes they're close enough to touch, if only for a brief, brilliant moment. The universe held its breath on August 17, 2017, as two dead stars performed the ultimate cosmic tango, a kilonova explosion that would revolutionize astronomy. What began as a faint ripple in space-time, picked up by LIGO gravitational wave detectors, soon erupted into a multisensory spectacle witnessed across the electromagnetic spectrum. Coded GW170817, this wasn't just another collision. It was the first time humanity caught two neutron stars merging in real time, offering front-row seats to the universe's most efficient goldsmith. For decades, theorists had predicted such events city-sized stellar corpses, each more massive than our Sun yet barely 12 miles wide, spiraling into each other at a third the speed of light. The reality proved even wilder, as these ultra-dense objects made their final 1,000 orbits in mere seconds. They stretched spacetime itself, emitting gravitational waves that reached Earth after traveling 130 million light-years. But the real fireworks began moments after impact, when the collision ejected a superheated jet of material glowing with the brightness of a billion suns. This produced both a short gamma-ray burst, a 2-second blast of high-energy photons, and an afterglow spanning X-rays to radio waves, painting the most complete picture of a kilonova ever seen. What unfolded next rewrote chemistry textbooks. Spectroscopic analysis revealed telltale fingerprints of heavy elements forged in the explosion's extreme conditions, particularly gold and platinum, with estimates suggesting the event created up to 10 Earth masses of gold alone. That's enough to alloy every piece of jewelry ever worn by humans. Here was conclusive proof that neutron star mergers serve as cosmic foundries, where rapid neutron capture, the R process, transforms ordinary matter into precious metals under pressures no lab on Earth could replicate. The aftermath resembled a celestial smelting furnace. Hubble observations showed expanding clouds of lanthanides and actinides, rare Earth elements cooling into infrared, emitting dust over weeks. Meanwhile, the merger's central remnant remained shrouded in mystery. Did it collapse into a black hole immediately, or briefly form a hypermassive neutron star before succumbing to gravity? Even today, debate rages about the ultimate fate of this cosmic wreckage. GW170817 did more than dazzle astronomers. It birthed an era of multi-messenger astronomy, where gravitational waves, light, and particles tell a unified story. This single event confirmed theories dating back to the 1970s while exposing gaps in our understanding of extreme physics. From gold's cosmic origins to the behavior of matter at nuclear densities, every second of this explosion offered a masterclass in universal alchemy, proof that sometimes the universe's most valuable treasures are born from its most violent crashes. In late 2019, astronomers noticed something unsettling. Betelgeuse, the red supergiant marking Orion's shoulder, was fading. By February 2020, it had dimmed to just 36% of its usual brilliance, the faintest it had been in over a century of observations. Panic rippled through the astronomy community. Was this the prelude to one of the most spectacular cosmic events in human history, a supernova visible even in daylight? For weeks, telescopes across the globe locked onto the star, while headlines breathlessly speculated about Earth's first naked-eye supernova since Kepler's in 1604. The excitement wasn't unfounded. Betelgeuse is a ticking time bomb, a star so massive it's already burned through its nuclear fuel in just 8 to 10 million years, a blink compared to our Sun's 10 billion-year lifespan. Models suggest it could explode any time in the next 100,000 years, and astronomical any day now. When it does, it'll outshine the full moon for weeks, casting shadows at night and possibly remaining visible for months. So when it suddenly dimmed, scientists scrambled to decode whether this was the final countdown. But the universe loves a good anticlimax. By April 2020, Betelgeuse began brightening again. The culprit, not an impending core collapse, but a colossal belch of stellar dust. High-resolution images from the Very Large Telescope revealed the star had ejected a cloud of superheated material that cooled into opaque particles, temporarily blocking its light from our perspective. It was a cosmic magic trick, an illusion of impending doom orchestrated by something as mundane as space dust. This event peeled back layers of mystery surrounding red supergiants. Betelgeuse's dimming exposed how little we understand about the final acts of these stellar behemoths. We now know they don't just fade quietly. They convulse in fits of mass loss, coughing up chunks of their own atmospheres in erratic outbursts. Some theorize the 2020 event was a preview of the star's death throes, not the main event, but a dress rehearsal for the real supernova to come. What's fascinating is how this scare transformed astronomy. For the first time, amateurs and professionals collaborated in real time across social media, sharing observations and theories as the drama unfolded. Betelgeuse became a global lab, demonstrating how modern science operates at internet speed. And while the supernova didn't arrive, the episode left us with a tantalizing thought. One night, perhaps sooner than we think, Orion's shoulder might vanish, replaced by a light so bright it rewrites human history. Until then, Betelgeuse keeps us guessing, a volatile reminder that the universe's grandest explosions often come without warning. The Vela pulsar doesn't just spin quietly in the cosmic dark, it's the beating heart of one of the most spectacular supernova remnants ever discovered. Located about 800 light-years away in the constellation Vela, this stellar corpse marks the spot where a massive star detonated roughly 11,000 years ago, in an explosion so bright our ancestors might have seen it glowing in Earth's night sky. Today, the debris from that cataclysm spans nearly 100 light-years, a shimmering web of gas and dust still expanding at nearly 40,000 miles per hour. But the real marvel lies at its center, a pulsar spinning 11 times per second, blasting out jets of X-rays and gamma rays so intense they sculpt the surrounding nebula into an eerie formation astronomers call the Hand of God. What makes this cosmic wreckage so fascinating isn't just its age, it's the sheer violence still unfolding within it. Chandra X-ray observatory images reveal a neutron star hurtling through space at over 700,000 miles per hour, its rapid rotation powering a wind of charged particles that collide with slower-moving debris. These collisions create shockwaves visible as intricate blue tendrils, while the pulsar's polar jets stretch light-years into space, bending and twisting like searchlights in a hurricane. The hand itself, a wispy structure of high-energy particles, appears to reach out from the chaos, though the shape is just a trick of perspective. What we're really seeing is a cosmic pressure cooker, where magnetic fields are 1 trillion times stronger than Earth's whip particles to near light speeds. Yet the Vela pulsar story goes deeper than its ghostly X-ray glow. Radio telescopes have detected strange hiccups in its rotation, sudden speed-ups called glitches that hint at turbulent dynamics inside the neutron star. Picture a city-sized ball of ultra-dense matter where the crust is rigid, but the interior flows like a superfluid. When these layers briefly uncouple, the star's spin jumps unpredictably, offering fleeting clues about physics under conditions impossible to replicate on Earth. Even more intriguing are the remnants' chemical fingerprints. Vela's expanding filaments shine with oxygen, neon, and magnesium elements forged in the progenitor star's final moments and now being recycled into interstellar space. Spectroscopic studies suggest the original explosion may have been lopsided, flinging debris unevenly like a broken cannon. This asymmetry gives the nebula its complex, shredded appearance, a frozen snapshot of the chaos that follows when stars die violently. Perhaps most remarkable of all is how close we are to this celestial wreck. Most supernova remnants of this age have dissipated into the void, but Vela remains vivid enough to study in granular detail. Its proximity lets astronomers watch the aftermath of stellar death in real time, the pulsar's winds carving new cavities, shockwaves heating gas to millions of degrees, and dust grains condensing in cooling ejecta. It's a rare glimpse into the life cycle of the elements, proof that destruction and creation are two sides of the same cosmic coin. The Vela pulsar doesn't just represent a star's end, it's a bridge between past and future. The heavy elements it scattered will one day seed new stars, planets, perhaps even life. And as it spins tirelessly in the wreckage, it reminds us that even in death, stars shape the universe in ways we're only beginning to understand. Most supernova remnants spread outward in elegant, symmetrical shells, but W49b laughs at symmetry. Located 26,000 light-years away in the constellation Aquila, this barrel-shaped wreckage looks more like a cosmic canister than a typical stellar explosion. Its bizarre geometry tells a story of violent asymmetries where a dying star didn't just explode. It detonated with such uneven fury that it may have birthed the Milky Way's youngest black hole. Chandra X-ray observatory images reveal the aftermath in startling detail. Instead of the usual spherical debris field, W49b's glowing gas forms two distinct lobes, pinched at the middle like an hourglass tipped on its side. Iron-rich material jets outward along the barrel's axis, while sulfur and silicon dominate the equatorial regions, clear evidence the progenitor star blasted material poleward with extraordinary force. This isn't just a messy explosion, it's a targeted eruption, the kind astronomers associate with gamma-ray bursts. The leading theory suggests the star's core may have collapsed directly into a black hole, funneling its death throes into ultra-relativistic jets that punched through the stellar envelope before the rest of the star could catch up. What makes W49b truly exceptional is what's missing. Most core collapse supernova leave behind a neutron star, a dense, spinning remnant detectable through X-ray pulses or radio waves. Yet despite exhaustive searches, no such object appears here. Instead, the region around the explosion's epicenter shows an eerie absence of compact emission, strongly hinting that the core may have skipped the neutron star phase entirely and imploded straight into a black hole. If confirmed, this would make W49b one of the clearest nearby examples of a black hole birth caught in the act, a stellar corpse weighing at least 10 suns crammed into a space smaller than Manhattan. The timing adds another layer of intrigue. Estimates place the explosion at just 1,000 years old, a newborn in cosmic terms. For perspective, when light from this detonation first reached Earth, humans were building medieval castles and navigating by the stars. That youth means the remnant structure hasn't been blurred by millennia of interstellar winds, offering astronomers an unusually pristine snapshot of hyper-asymmetrical stellar death. Radio observations even detect molecules like hydroxyl masers forming in the cooling ejecta, a sign that the chaos of destruction is already giving way to the chemistry of new beginnings. But the most tantalizing question remains, was this a failed gamma-ray burst? The jet-like distribution of heavy elements suggests W49b's progenitor could have produced a GRB had its poles been aimed at Earth. Instead, we see it from the side, a quasar's eye view of what might have been the most energetic explosion in our galactic neighborhood. It's a humbling reminder that the universe often hides its greatest fireworks just out of sight, reshaping entire galaxies while we catch only the faintest echoes of their power. W49b doesn't just challenge our understanding of stellar deaths, it redefines them. Here lies proof that stars don't always bow out gracefully, sometimes they end in directed violence so extreme it warps the very geometry of their remains. As we study this cosmic oddity, we're not just mapping the fate of one star, we're decoding the birth cries of black holes and the hidden links between supernova and the universe's most luminous explosions. And that makes this lopsided remnant one of space's most eloquent teachers. GRB 110328 wasn't just another gamma-ray burst, it was a cosmic horror show playing out in real time. Detected on March 28, 2011, this explosion refused to fade like a typical burst. Instead, it flickered back to life again and again, pulsing with X-ray flares for weeks like a dying star refusing to stay dead. Astronomers quickly dubbed it the zombie star, but the truth behind its persistence was even more unsettling. This was the signature of a supermassive black hole ripping apart a nearby star in a tidal disruption event, a rare cosmic feeding frenzy broadcast across the universe in high-energy radiation. What made this event so extraordinary was its extended drama. Most gamma-ray bursts last from milliseconds to a few minutes, their brief flashes marking the death throes of massive stars or neutron star collisions. GRB 110328 defied all expectations by flaring repeatedly over 2.5 months, its X-ray emissions surging and fading like the ragged breaths of a mortally wounded celestial beast. The SWOPE supernova survey, which first pinpointed its location in a small galaxy 3.8 billion light-years away, captured these eerie fluctuations, revealing a light curve unlike anything seen before in high-energy astrophysics. The culprit, a star that wandered too close to a lurking supermassive black hole, one weighing millions of suns, and found itself torn apart by tidal forces. Imagine the star stretched like taffy, its outer layers shredded into a swirling disk of superheated gas spiraling toward oblivion. As this stellar debris fell toward the event horizon, it generated shock waves that produced the initial gamma-ray flash, followed by violent X-ray outbursts whenever fresh chunks of the star plunged into the accretion disk. Each flare carried the star's dying screams, its matter compressed and heated to billions of degrees before vanishing into the black hole's maw. But the real surprise came when astronomers traced the explosion's origin. Unlike typical GRBs linked to collapsing stars, this one erupted from the center of its host galaxy, the exact neighborhood where supermassive black holes lurk. Hubble observations later confirmed the presence of an active galactic nucleus, its voracious appetite briefly supercharged by this stellar snack. The data painted a grisly picture, a sun-like star shredded over months, its remains lighting up the cosmos with the violence of its disassembly. What makes GRB 110328 so groundbreaking isn't just its brutality, it's the new window it opened onto black hole behavior. Before this event, no one suspected tidal disruptions could mimic gamma-ray bursts so precisely. Now astronomers scour old data for similar fake GRBs, realizing these cosmic masquerades might be more common than anyone imagined. The zombie star's prolonged death throes revealed something even more profound. Black holes don't always dine quietly. Sometimes they announce their meals with fireworks visible across the universe, turning a star's destruction into a beacon that illuminates the darkest corners of spacetime. This bizarre explosion blurred the lines between known astrophysical phenomena, proving that the universe loves to defy categorization. It's a reminder that for every cosmic mystery we solve, a dozen new ones emerge, each more unsettling and wondrous than the last. On June 16, 2018, astronomers spotted something utterly bizarre. A flare of light in galaxy CGCG 137068, located 200 million light-years away, that defied all known cosmic explosion templates. Code-named at 2018 Cow, or simply the Cow, this anomaly brightened 10 times faster than a typical supernova, reaching peak luminosity in just 2 days before fading into a peculiar blue glow. But speed wasn't the only puzzle. Unlike normal stellar explosions rich in hydrogen and helium, the cow's spectrum revealed almost no traces of these common elements, instead glowing fiercely with heavy metals and strange, unidentified emission lines. For weeks, telescopes worldwide swiveled to observe this celestial oddity, sparking debates that continue to this day. Had astronomers witnessed the violent birth of a black hole, the shredding of a star, or something entirely new? What made the cow so electrifying was its unprecedented energy profile. Most supernovae fade gradually as radioactive decay powers their glow, but this event's light curve dropped off a cliff after its initial spike, suggesting an entirely different engine driving the explosion. X-ray emissions flared erratically, pulsing with a rhythm that hinted at a central power source, likely a newborn black hole or neutron star devouring surrounding material. Then there was the color, an intense, almost unnatural blue hue indicating temperatures exceeding 27,000 degrees Fahrenheit, far hotter than typical supernova remnants. The more data poured in, the clearer it became this wasn't just an unusual explosion. It was a new class of cosmic event altogether. Theories erupted as wildly as the cow itself. Some proposed it was a failed supernova, where a massive star's core collapsed directly into a black hole without the usual explosive finale. In this scenario, the star's outer layers would have funneled into the newborn singularity, creating a brief but dazzling accretion disk flare before vanishing into darkness. Others pointed to a tidal disruption event, a star torn apart by a black hole. But the cow's location far from its galaxy's center made this unlikely, the most tantalizing hypothesis. A blue supergiant star being devoured from within by a newborn black hole, its core imploding while the outer layers briefly resisted, creating a shockwave that lit up like a cosmic neon sign. Perhaps the most compelling clue came from radio observations. The Very Large Array detected particles accelerating to near light speed around the object, behavior typical of compact remnants like neutron stars or black holes. Meanwhile, Hubble spotted evidence of dense material surrounding the explosion site, possibly a cocoon of gas ejected by the progenitor star before its demise. This could explain the lack of hydrogen in the spectra. The star had already shed its outer layers, leaving only its metal-rich core to light up the fireworks. The cow's legacy isn't just about solving a single mystery. Its discovery forced astronomers to confront how much we still don't understand about stellar death. Since 2018, similar fast blue optical transients F-BOT have been identified, each sharing the cow's peculiar traits: rapid brightening, strange spectra, and evidence of central engines. These events suggest an entire family of cosmic explosions exists between the well-mapped territories of supernova and gamma-ray bursts, hiding in plain sight until now. What lingers isn't just scientific curiosity, but a humbling realization. For all our telescopes and models, the universe still coughs up phenomena that defy textbooks. The cow didn't just illuminate a distant galaxy, it exposed the gaps in our cosmic maps, proving that even in death, stars have secrets we're only beginning to uncover. And somewhere out there, another anomaly is waiting to rewrite the rules all over again. October 9, 2022, started as an ordinary day for astronomers until the cosmos unleashed GRB 221009A. A gamma-ray burst so blinding it earned the nickname the BOAT, brightest of all time. Detected by satellites across our solar system, this explosion from 2.4 billion light-years away unleashed photons packing 18 tera-electron-volts of energy, more powerful than anything ever recorded from such a distant source. Within minutes, automated alerts lit up observatories worldwide as scientists realized they were witnessing something unprecedented. a burst so intense its afterglow outshone nearly every X-ray source in the sky combined, including pulsars that had dominated the high-energy landscape for decades. The numbers behind this cataclysm defy comprehension. For 300 seconds, an eternity in gamma-ray terms, the burst saturated detectors with photons carrying the combined energy of 30,000 suns. Its total radiation output surpassed a typical supernova by 1,000 times, making it temporarily the brightest object in the observable universe outside our solar system. Even more astounding was its impact on Earth. As the gamma rays hit our upper atmosphere, they ionized atoms across the planet's sunlit side, distorting long-wave radio communications in a phenomenon usually associated with solar flares. Instruments normally tuned to study Earth's ionosphere suddenly found themselves tracking radiation from another galaxy altogether, a first in scientific history. What caused this record-breaking detonation? While most gamma-ray bursts stem from collapsing stars or neutron star collisions, GRB 221009A's extreme energy points to a hyper-rare magneto-rotational supernova. Picture a rapidly spinning, highly magnetized star collapsing into a black hole, its rotational energy funneled into twin relativistic jets by magnetic fields trillions of times stronger than Earth. This cosmic particle accelerator then blasted material at 99.999% light speed, focusing its energy into beams narrower than a degree across. Had one of those jets pointed directly at Earth, the results could have been catastrophic. Even at its vast distance, the burst delivered enough energy to temporarily alter our planet's atmospheric chemistry. The aftermath proved equally astonishing. For weeks, space telescopes tracked a slowly fading afterglow across X-ray, optical, and radio wavelengths, a signature of shockwaves plowing through interstellar gas at relativistic speeds. Particularly puzzling were erratic brightness fluctuations, suggesting the newborn black hole was still being fed by falling debris in fits and starts. Meanwhile, spectral analysis revealed telltale signatures of heavy elements like gold and platinum forged in the explosion, confirming these events as cosmic crucibles for the universe's rarest metals. Perhaps most humbling is what GRB 221009 represents statistically. Based on current models, bursts this luminous should occur only once every 10,000 years in our observable universe. That we witnessed one in the brief era of modern astronomy suggests either incredible luck or that our understanding of these explosions remains dangerously incomplete. As astronomers continue sifting through petabytes of data, one truth emerges: space reserves its most violent spectacles for those patient enough to watch the skies and bold enough to question what they think they know. Deep in the heart of our Milky Way, near the supermassive black hole Sagittarius A, astronomers have detected something startling: violent bursts of energy marking the annihilation of antimatter on an astronomical scale. These aren't your typical cosmic explosions. When antimatter meets normal matter, they obliterate each other in a flash of pure energy, converting mass directly into gamma rays with 100% efficiency, a process far more destructive than any nuclear reaction. The Fermi Gamma Ray Space Telescope has mapped these annihilation events, revealing plumes of radiation stretching thousands of light years from the galactic center, where the equivalent of billions of tons of antimatter appears to be colliding with normal matter every second. The mystery isn't just the scale of these explosions, it's their origin. Antimatter shouldn't exist in such quantities naturally. According to everything we know about particle physics, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other long ago, leaving behind nothing but energy. Yet here we are, in a universe made of matter, with unexplained pockets of antimatter detonating near our galaxy's core. One leading theory suggests exotic processes around the supermassive black hole might be generating fresh antimatter, perhaps through particle collisions in its accretion disk or the decay of hypothetical dark matter particles. Speaking of dark matter, this shadowy substance might hold the key to the puzzle. If dark matter consists of weakly interacting massive particles WIMP, their mutual annihilation could produce antimatter as a byproduct. Imagine invisible dark matter particles colliding after being funneled toward the galactic center by Sagittarius A's gravity, their destruction sparking secondary explosions we detect as gamma-ray flares. Supporting this idea are strange excesses of positrons' antimatter electrons observed in cosmic rays, which align with models of dark matter decay. But there are other, equally fascinating possibilities. Some astrophysicists argue these antimatter fireworks could stem from pulsars, rapidly spinning neutron stars whose intense magnetic fields might accelerate particles to energies where antimatter spontaneously forms. Others point to microquasars, smaller versions of active galactic nuclei that could be ejecting antimatter jets. Then there's the wild card, quantum fluctuations in the vacuum of space itself, where particle-antiparticle pairs briefly flicker into existence. Normally, they annihilate immediately, but near a black hole's event horizon, one particle might fall in while the other escapes, creating a net surplus of antimatter. What makes these detonations so scientifically precious is their diagnostic value. Every gamma-ray photon carries information about the annihilation process that created it, allowing us to reconstruct the antimatter's properties like cosmic forensic scientists. Recent analyses suggest the antimatter isn't uniformly distributed but clustered in filaments and bubble structures that shouldn't persist long unless continuously replenished. This points toward an ongoing production mechanism rather than some ancient reservoir of antimatter left over from the Big Bang. The implications stretch far beyond astrophysics. If dark matter truly generates these explosions, studying them could reveal its composition, a holy grail of modern physics. Alternatively, if the antimatter arises from black hole dynamics, it might offer new insights into how these gravitational monsters reshape their surroundings. And should we discover some entirely new antimatter production process, it could rewrite textbooks on particle physics and cosmology alike. For now, the antimatter explosions near our galactic center remain one of astronomy's most tantalizing puzzles. A reminder that even the most destructive events in the universe can shed light on its deepest mysteries. Each gamma-ray flash is both a question and a clue, drawing us closer to understanding the invisible forces shaping our galaxy and perhaps the very nature of reality itself. On December 27, 2004, Earth's upper atmosphere suddenly lit up with ionized particles, not from a solar flare, but from a cosmic detonation 50,000 light-years away. Magnetar SGR 180620, a city-sized neutron star with the mass of 2 suns, had just unleashed the largest stellar flare ever recorded, a starquake so violent its gamma-ray pulse momentarily outshone the entire Milky Way. For 0.2 of a second, this exotic object released more energy than our Sun emits in 250,000 years, a burst so intense it punched through Earth's magnetic field and measurably altered our ionosphere from across the galaxy. What makes magnetars unique isn't just their density. A sugar cube-sized chunk would weigh 1 billion tons, but their unimaginable magnetic fields. SGR 180620's magnetic grip measures a quadrillion times stronger than Earth's, so powerful it distorts the very shape of atoms and creates a crust under constant strain. When this crust finally fractured under magnetic tension, the resulting starquake triggered a relativistic avalanche. Twisted magnetic field lines snapped like overstretched rubber bands, flinging electrons at near-light speed through surrounding plasma. These spiraling particles then emitted gamma rays through synchrotron radiation, a process so efficient it converted the magnetar's pent-up energy into the most concentrated electromagnetic burst ever observed. The explosion's aftermath revealed even stranger physics. Unlike a supernova's expanding debris, the magnetar's flare left no visible remnant, just an invisible afterglow of polarized X-rays, proof that the energy had been channeled along precise magnetic pathways. Satellite data showed the initial spike contained oscillations matching the neutron star's rotation period, essentially turning the entire magneta into a ringing bell of pure gamma radiation. For weeks afterward, the star's magnetosphere shimmered with aftershock pulsations, like ripples from a stone dropped into a pond of spacetime itself. This event didn't just break records, it redefined astrophysical limits. Had SGR 180620 been within 10 light-years instead of 50,000, its flare could have triggered mass extinctions by stripping Earth's ozone layer. Yet paradoxically, magnetas may also be galactic life-givers. Their eruptions forge rare isotopes like technetium and promethium, elements later incorporated into new stars and planets. That a single stellar corpse can simultaneously threaten and nurture life across cosmic timescales is a humbling reminder. The universe's most destructive forces are often the architects of its greatest creations. Hidden in the constellation Ophiuchus lies a cosmic crime scene so vast it could hold 15 Milky Ways side by side, the aftermath of the largest explosion since the universe began. Astronomers first dismissed the faint X-ray flickers as instrument noise, but closer inspection revealed something unimaginable: a titanic cavity in the hot plasma surrounding the galaxy cluster MS-073 5.6+7421, a gaping void spanning 1.5 million light-years carved by a black hole's tantrum of unfathomable proportions. This record-breaking eruption traces back to a supermassive black hole weighing billions of suns lurking at the cluster's heart. Unlike typical black holes that nibble on passing gas, this monstrosity went berserk, devouring entire stars and belching out jets of plasma at near light speed. The energy released 5 times greater than the previous record holder, equals 10 billion supernova exploding simultaneously, a sustained outburst lasting perhaps 100 million years. Imagine a volcano the size of a solar system erupting for eons, its fury sculpting bubbles in the fabric of space itself. What makes this explosion so extraordinary isn't just its scale, but how it's rewritten our understanding of black hole physics. The cavity's sheer size suggests the black hole wasn't just recycling nearby matter. It must have gorged on an unprecedented feast, possibly triggered by a collision with another galaxy cluster that funneled galaxies' worth of gas into its maw. Chandra X-ray observatory data reveals shimmering ripples in the cluster's plasma, like sonic booms from the explosion's shockwaves still traveling outward after 100 million years. These pressure waves heat surrounding gas to hundreds of millions of degrees, preventing it from cooling and forming new stars, effectively sterilizing an entire galactic neighborhood. Yet the most puzzling aspect isn't the energy output, but the black hole's efficiency. Somehow, this gravitational monster converted raw material into focused jets with nearly perfect precision, channeling chaos into directed violence on a cosmic scale. Researchers estimate the jet's power output exceeded the entire cluster's light output by a factor of 10, a reminder that black holes don't just consume, they transform matter into the universe's most destructive fireworks. The Ophiuchus explosion's legacy lingers in the ghostly afterglow of radio waves, where electrons spiraling along ancient magnetic fields still whisper tales of the eruption. For astronomers, it's a humbling corrective proof that even our wildest theories about cosmic power pale next to reality's capacity for violence. And somewhere out there, another sleeping giant waits, biding its time before reshaping the cosmos once more with a yawn of pure annihilation. At the farthest edges of theoretical astrophysics lies an explosion so extreme it makes black holes seem tame. The quark nova. Picture a neutron star, already one of the densest objects in existence, subjected to pressures so insane its neutrons shatter like glass. This isn't just collapse, it's the universe breaking matter itself down to its most fundamental ingredients, triggering a detonation that could outshine entire galaxies in raw energy output. While no confirmed quark nova has ever been observed, the mathematics suggest such an event wouldn't just rewrite the rules of stellar death, it would erase the rulebook entirely. The chain reaction begins inside a neutron star's crushing interior, where gravity has already compressed matter beyond atomic structure. Here, protons and electrons have long since merged into neutrons, creating a sea of ultra-dense particles just barely resisting further collapse. But if conditions tip past a critical threshold, perhaps from absorbing extra mass or through quantum fluctuations, those neutrons might disintegrate into their component quarks. Suddenly, the star's core transforms into a plasma of free-floating up, down, and strange quarks, a state of matter so exotic it defies earthly comparison. This phase transition releases more energy per second than the Sun will emit in its entire lifetime, as the star's outer layers rebound off the newly formed quark core in a shockwave of unprecedented violence. What makes this hypothetical explosion so terrifyingly efficient is quark matter's properties. Under these extreme conditions, quarks might form a perfect fluid with zero viscosity, a substance that flows without friction, allowing energy to propagate almost losslessly. The resulting fireball could reach temperatures of 1 trillion degrees, briefly making it the hottest spot in the observable universe. Gamma rays from such an event would carry spectral signatures unlike anything seen in supernova or kilonovae, likely dominated by strange quark interactions that don't normally occur in nature. Some models even suggest the explosion might emit gravitational waves with a distinctive frequency pattern, a telltale scream of quarks being liberated after billions of years of confinement. The aftermath poses even wilder possibilities. A quark nova wouldn't leave behind a black hole or neutron star, but a quark star, an object so dense its very existence challenges our understanding of quantum chromodynamics. Observations of certain ultra-bright supernova with unexplained energy spikes, like SN 2006 GY, have led some theorists to speculate we might have already witnessed quark nova without realizing it. Others propose that these explosions could solve the mystery of fast radio bursts, those millisecond cosmic radio pulses whose origins remain debated. If even a fraction of these phenomena stem from quark-level detonations, it would mean the universe harbors explosions operating on a scale we've barely begun to imagine. Perhaps the most mind-bending implication lies in quark nova's potential role in cosmic alchemy. While supernova forge elements up to iron and neutron star mergers create heavier metals like gold, a quark nova's unique conditions might produce strangelets, clusters of strange quarks that could transform normal matter upon contact. This raises the eerie possibility that such explosions don't just destroy, they might mutate the fabric of reality itself, seeding the cosmos with exotic matter that behaves unlike anything in our periodic table. Until we detect definitive proof, perhaps through gravitational wave observatories catching the vibration pattern of a collapsing neutron star or a telescope spotting the unmistakable light curve of quark matter formation, the quark nova remains the ultimate what-if of astrophysical detonations. It's a reminder that despite all we've learned about cosmic explosions, the universe likely holds ultraviolent spectacles we haven't even dreamed of yet. And somewhere out there, in the dark between galaxies, a neutron star might be teetering on the brink of the most extreme transformation matter can undergo, not death, but deconstruction into the universe's rawest, most primordial form. From the universe-shattering fury of the Big Bang to the eerie whispers of antimatter annihilations near our galaxy's core, these 25 cosmic explosions redefine what it means to unleash pure energy. Each detonation, whether a magnetar's starquake vibrating space-time or a black hole's billion-year tantrum carving voids in galaxy clusters, stands as a testament to forces beyond human scale. GRBs brighter than entire galaxies, hypernova vaporizing stars from the inside out, and kilonovae forging celestial gold in their wake, these aren't just events. They're the universe's way of sculpting itself, forging elements, and occasionally reminding us how fragile our corner of existence truly is. Consider the echoes lingering from these cataclysms. The Crab Nebula's pulsar still spins like a lighthouse 11,000 years after its progenitor star exploded. The light from SN 1054, witnessed by Song Dynasty astronomers, now illuminates Hubble's lenses as expanding debris. And somewhere in the void, the shockwaves from the Ophiuchus supermassive black hole's eruption continue rippling through intergalactic gas, a silent tsunami of energy older than humanity itself. These explosions aren't just past events, they're ongoing processes, their aftermath shaping the chemistry of future stars, planets, and perhaps life. Yet for all we've documented, the cosmos guards even greater spectacles. Will we witness Betelgeuse's inevitable supernova, a daytime star visible for generations? Could a quark nova rewrite physics before our telescopes? Or will Earth's atmosphere someday sizzle under a gamma-ray burst's lethal kiss? The universe specializes in surprises like GRB 221009A, the boat, blindsiding us with energies previously deemed impossible. Every new detection peels back another layer of cosmic ferocity, proving that for every question answered, 10 more explosions defy explanation. So as we look up at the tranquil night sky, let's remember that darkness is an illusion. Beyond the quiet twinkles lies a reality of unimaginable violence, and somewhere out there, the next record-breaking detonation is already brewing. The only uncertainty, whether we'll be here to see it or become part of its aftermath. The universe doesn't care about our calendars or clocks. Its explosions operate on timescales spanning microseconds to eons, in energies ranging from a star's whisper to a black hole's scream. And so we're left with a humbling thought. In a cosmos this volatile, are we the observers or just future stardust waiting for the next great blast?